test. Mic test, mic test, mic test. Hello, hello. Mic test. Hi. My mic is not working. Mic test, mic test, mic test, mic test. Mic test, mic test. Hello, hello. Mic test. Mic test. Can you hear me?
Yes.
Oh, you can hear me?
Yep.
Okay, good, good, good. Okay, right. That's good. Let me see what else can I do. My volume a little bit.
I cannot.
Let's just give a few more minutes. Hello, hello. Let's just give a few more minutes. I'm going to send an invite link. I think I sent and try to add.
How is you watching from Jibes? Is it? Isn't it?
I think he also has a laptop.
Wait, let me check.
Can y'all try to post the questions and see whether I can see?
Oh, you're using Windows, so might be remote access.
No, some of you seem to be types.
Laptop.
Okay, we'll start in a few minutes. Okay, just hold on for a while.
Move to the server.
Yeah, actually. Cool.
Yeah, okay.
Where are you watching?
I'm not watching it because I don't have my laptop.
Oh,
My LCD is gone.
your LCD is gone. Oh shit.
I'm getting it replaced.
You could maybe. Sorry? Mute your microphone.
Okay, let's see. Okay, can I just check again? Wait, whether you can hear me?
Yes.
Okay, yes, right. If you can hear me,
Yeah.
just give me a thumbs up or something. I can see some of you. For example, I can see Sudip, and then I can see uh Gopala Krishnan and
Yeah.
all. Yeah, right. Okay, good. Hi. Sorry, give me a minute. Hi. Hey, are we? I hope so. Some of them are on, right? I sent you the invite. Do you want to join us? And you didn't see the link. I just sent an email separately. Yeah, I sent an email. Thank you. Can you check the? You want to join? Oh, I just sent the link actually. Yeah. Hi. Yeah. Uh, let's just give a few more minutes for people to log on. Yeah, it's the first time we're doing this. Actually, quite fun actually. Um, let me see. Can you see the slides? Hi.
Yep.
Right. Right. Okay. So you can see the slides. Can somebody try to ask a questions on see whether it can appear right now? I don't see any questions. I just want to see whether we can have questions on. Oh, I don't see a questions actually. Let me see Q&A. Everything is live. Okay, there's a chat. Please speak louder. Okay. Um, right. I hope you can hear me. Fu Dang Bang. Right. I hope you can hear me now. Let me just increase the volume a bit here. Right. Yeah. Okay. Good. 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 It's good to see. Okay. So good to see you. Right. Let's give it um another 2 3 minutes. Right. Hi. Awin Khan. Hello. I see. Thanks a lot for your help. Um, okay. Okay. Right. I've 10% just joining. Give me a minute. I need to share the YouTube link with with the others so everybody can follow. Okay. Okay. That's one. Okay. Last one, right? Okay, right, I think let's start. Okay, so actually I have 10 students who are on Hangout now, right? And then the rest are not. Okay. Let me start with the YouTube with the recording. I hope everything is fine. Right. Send me YouTube link. I just sent. Okay. Okay. Fine. Hopefully, yeah. If Arwin have some problem, I think most of the other students will have problem too. All right. Sorry for the delay. Well, so for today, we want to talk about data flow graph, right? Essentially, the set of slides is posted on NTU on our website. Um, so I'm going to walk you through, right? I've shared the set of PDF, right? The first thing we want to look at is to come up with a model, right? To uh, to to have a systematic way, right, to look at a system. So a data flow graph is one such model. We could look at it from a timeline perspective. We could look at it from a resource perspective, right? Edward Lee says it that the model is the artifact that imitates the systems, right? So essentially what we are trying to do is to model systems and therefore understand the characteristics better. Model has syntax, it has semantics, okay. They are supposed to help us to understand the system better and therefore be able to to reason and analyze better. Okay, so that's the idea of trying to look at models. All right. So when we look at hardware, what is so different with just looking at it from a software's perspective, right? A model is really a theoretical study, so to say, right? But what we are trying to do is to come up with a realistic model that can be applied to hardware, and this is often hard to do, right? Hardware is often modular, hierarchical, which you will see in your Verilog design, right? And hardware is typically spatial, right? In terms of computational blocks, and you'll find that when you use a hardware systems, the functional blocks that you want to use, right? They have to be active or live, right? For those blocks that you are not using, you will try to turn it off to save power, right? Let's use an example of a circuit system diagram, right? What we have here is um, a bunch of logic gates, right? You can see that there's a labeling of 1, 2, 3, right? Right, there's a labeling of 1, 2, 3, 4, and 5, right? What this does is basically, if I look at it from timing and analyzer perspective, right? Um, we are actually trying to look at the propagation timing. I mean, one way is to take it from a timing analyzer perspective. Yeah, the input to output propagations, right, through the two input AND gates, right? Then that joins to a two input OR gate, right? And that is the third order. Why is that a third order? Because one of the input come from a second stage two input AND gates, right? So if I look at it in terms of timing, essentially the worst case will have to propagate through 5 logic gates, right? A NOT gate, an AND gate, a OR gate, a OR gate, AND gate, then comes to the output, right? That's why we come up with the labeling 1, 2, 3, 4, and 5. Okay, so well, another thing to take note of in this circuit diagram is there is no clock. Okay, this is a pure clockless diagram, or what we call asynchronous system design. Asynchronous design, when you change the input, you expect the output to change, right? So an input change, right, is an event that results in the output change. Okay, So it is basically asynchronous, does not depend on the clock. So the clock is not useful in such a design. Okay, and in this kind of systems, what we are really concerned is what is the total propagation delay from input to output, right? When I change the input, how much time does it take for the changes to propagate to the output, right? So, oh, okay. Okay. Let me, I just received a email from, let me just see. Sorry for the distractions. Okay, right. Seems like we are live, right? And then because I've been okay, good, fine. Let's continue. Uh, oh, so you can ask me questions on the on the Q&A panel. You can also ask me questions on the YouTube link. Yeah, so feel free to ask questions, and then I'll try to answer them um, as best I could. Okay. Okay, so coming back to this diagram, right, the labeling 1, 2, 3, 4, 5 is really to look at the hierarchy. So you can see that essentially there is a order to this. Okay, that's also one thing to note. If you write in a nested if loop, right, so the more nests that you have, right, the higher the order. Okay, this evening during the tutorial, I will likely show you an example to illustrate this point. Okay, now, when we look at a digital systems, especially in FPGA, what we do is, well, in order to meet the timing, right? In order to meet the timing in a high-speed systems or a relatively high-speed systems, what do I mean by a high-speed systems? That is 2 to 300 megahertz or more, typically. Okay, when we want to mitigate timing in a high-speed systems, one of the common practice is to register the inputs that comes to my functional block, right? So I have a bunch of logic gates. Okay, forget about the registers in the middle first, right? Just refer to the registers at the input, the registers at the output. Okay, in it is a good practice, right, in digital design, okay, in FPGA to want to register the signal that's coming in and register the signal that's going out. Okay, you'll find that in a digital systems, the systems can be very complicated, very big, a few million gates or more, right? And in such a system, it is very hard for one digital engineer or a system engineer to do the whole systems. So what happens is that it will usually be taken charge by a lead engineer or principal engineers, and then under under the control of the principal engineers, there'll be a few senior engineers, and there'll be maybe 2 to 3 senior engineers, and there could be 7 to 8 fresh engineers who are learning the ropes, right? And then the fresh engineers will be given a block to design, maybe a USB block or a UART block or whatever, so a functional block, right? So, and after the engineer has designed that, he needs to integrate it into the system, right? So at the system integrations part, assuming you have a functional block like what you have here, in this case, the functional block is very simple, just a bunch of logic gates. That functional block, when you integrate to other functional block, right, there could be a serious propagational delay from the previous functional block to this block, right? So the interface between the functional block is something that you don't really know, right? So therefore, it is actually prudent, right, from a system perspective, when you design, right, you always try to register the signal that comes to your block. Okay, so that's why we want to have input registers so that we mitigate, right, any potential serious delay that comes to our inputs from the previous stage. All right, that's the reason. Likewise, it is also prudent to have a registers, okay, to the next stage. Okay, and that's why we usually have a input output registers. Okay, so that's what I want to say. Okay, and you'll find that, okay, what's the purpose of adding a registers? What is a register? Right, a register basically is a single clock cycle delay. It remembers, right? So at the rising clock edge, the output value will take the input value. So basically, it kinds of remember that value for one clock cycle. Okay, that's the whole idea of registering. Okay, and well, so I have my functional diagram. Well, what I could also do is, well, I could see that, hey, this whole diagram, okay, takes from input to output, assuming it takes a certain number of clock cycles. Okay, if I look at the timing analyzers, it might tell me that it takes 10 nanoseconds. Right, I like to use round number because it's easier to relate. So from input to output, it takes, let's say it takes 10 nanoseconds. It means that these systems can run at 100 megahertz. Right, so potentially, okay, assuming this is the critical path, right, these systems could run at 100 megahertz or 10 nanosecond clock period. Okay, in order for my input to go to my output correctly. All right, now if I want to speed up these systems, what I could do is I could say that, okay, let me add a register in the middle, essentially a pipe, right? By adding this pipe, what I'm doing is I'm breaking up the the logic operations into two clock cycle, right? First stage, second stage, clock cycle 1, clock cycle 2. Okay, I break it up into 2 cycles, so it takes 2 cycles for me to get my results. All right, now let's make it simpler again, right? Assuming that the delay from input to the intermediate register is 5 nanoseconds, from the intermediate registers to the output register is 5 nanoseconds. So now the worst case delay is just 5 nanoseconds, right? What it means is that, well, now I can run my systems at 200 megahertz, right, compared to previously, right? But then from input to output, right, it will take me 2 clock cycles, right? Nothing has changed, but I can push the clock to 200 megahertz. Okay, so that is the idea of adding a pipe. Okay, so, well, this is to get you familiarized with looking at circuit diagram, right? So this is basically the background that we want to build up to the data flow graph. Okay, right? So we could be building from gates, we could be building from discrete logic chips. This is getting rarer now, right? Because the 74,000 and so on discrete components, you still use that in some industries like automotive and automated test equipment, ATE. But we are really moving away from discrete logic chips, partly because it's costly. That's number one, right? Each of the chip costs money. It takes up real estate on the PCB board, right? So if you really want to streamline, cut down the size of a PCB, and you could actually implement many of these functional blocks, many of these functions in a FPGA, for example, right? Years ago, when I was working in Agilent, one of the job that I did was actually to combine many of the discrete components into FPGAs. Yeah, and that basically save ballpark figures. Okay, so you can find that implementation on FPGA is a way that has been going on for many years now. So to describe hardware systems, okay, we want to capture the the set of inputs and outputs, a set of functional blocks, right? Connection between the ports and so, okay, so just for you to see this, right? Now let's apply it to a systems, right? So you typically want to see how can I relate a data flow diagram to a system. So in your case, the project, you have a RF front end, the audio uh, synchronizer, right, to make sure the signal is acquired properly, right? Then you do your FFT, right? Then you have your filtering, right? And then after that, the modulation, so that you display onto your display. Each of the block is a functions or subsystems, right? They can be active at the same time. In your case, the blocks will be active at the same time, right? Uh, so it's a live stream unless you try to not to. Uh, each block compute so basically receive the input, compute, and send it to the output. Okay, the blocks may vary in complexity, the number of inputs, and rates of computations. So we may want to annotate the edges to describe what is being passed from one block to the next functions. Okay, and so mathematically you could have a functions, right? That is there's parameters where V is the set of nodes and then E is a set of directed edges. Okay, So you expect that the nodes would consume data, right? And then the nodes will also produce data. So it takes in data, compute on it, send data out, right? So it's an input-output node. Okay, and then you expect some computations to happen in at the node. Okay, and that's about that. Okay, so a node. So what we are trying to do is trying to look at the systems and applying a model onto it. That is the idea. Okay, so use an example. Okay, if I have a complex multiplications, in this case a plus bj, okay, and c plus dj, right? A and c are real, b and d are imaginary parts. If I multiply them together, I will expect j squared would be equals to -1, right? And therefore I will get a um, real portions ac minus bd, and then imaginary portions ad plus bc. Okay, so how do I do these computations? Okay, that's the questions I would ask myself, right? I have four inputs basically: a, b, c, and d, right? B is imaginary, d is imaginary, a and c are real. Okay, so if I draw a data flow graph, right, and I'm jolly well remember that I have four inputs, right? B representing the imaginary and D representing the imaginary. If I want to do a multiplication of this, what I could do is therefore multiply A with C, B with D, right? And then A with D and B with C. Subsequently do the subtractions, okay? AC minus BD so that I get my real, and then AD minus BC to get my imaginary additions. I'm sorry, not minus, additions. Okay, and that's what we saw in the previous equations. Okay, so just to recap, right, I have four input datas, A, B, C, D. Okay, four multiplications between the real and imaginary parts. Okay, and then I also have two adders, right, or rather products, right, add or subtract. Okay, right? And then each node can fire when its input operands are available, right? Basically, these are the resources I expect to use. Four multipliers, right? One adder, one subtractor, right? Okay, so in order to get my results. So relating it to the Verilog code, right? So this Verilog code is there's no clock, purely asynchronous, right? And that's why always at star. Basically, the star means that the inputs, what are the inputs? The inputs are A, B, C, D. When any of the input change, okay, this procedural block will trigger. Okay, this procedural block will trigger, and the computation will therefore kicks off, right, sequentially, right? Mod 1 will basically equals to A times C, like what we see. Okay, the multiplier will comes out with the result, which we call it mod 1. Okay, and then B times D is a second multiplication, which we call mod 2. Okay, and then so each of these will execute sequentially, actually, in a sequential block like this. Okay, but okay, in hardware, right, you really expect them to be actually running concurrently. If you have four multiplier, if I have four multiplier, I expect AC multiply give me this, right? Almost simultaneously, B and D multiply will give me a result mod B. Okay, the results of the two multiplier will then go to the subtractor. Okay, whereby mod 1 minus mod 2 will give me the result. Okay, but it's purely asynchronous, no clock informations. Okay, so this would create a circuit with one block per node. Okay, and connections are as shown in the edges. All right. So example is simple. Each node consumes one data token, so it takes in one data and then generates the data. No control informations, right? Because the input output is clearly defined, right? There's no timing that. So basically, just the inputs are very well defined. There is no change of input. Likewise, there is no change in the output. So there is a clear mapping of the nodes to the computational structures. Okay, so but then, okay, we have to ask ourselves, right? What if we have fewer resources available than we actually require? Like in this case, right? We require four multipliers and one adder, one subtractor. Okay, so what if we have less than that, right? What if we have less than that? Okay, so to do more structured models, right? You could be looking at control data flow, okay, can't process synchronous data flow, which we are not going to do, and I'm not going to cover. Okay, in this introductory course on data flow, right, what we are really trying to get you to do is to see how to use the data flow graph in your systems analysis, okay, to help you better manage the resource and timing. Okay, that is what we're trying to do. We're looking at it from an application perspective. Okay, so but of course there are more structured formal models that you could refer to, and we encourage the interested students to look at that, right? Especially if you are doing your postgraduate studies research on this, right? You could do that. Okay, so we're putting it here for completeness. Okay, you can refer to that, right? Coming back, okay, let's say I ask myself, right, in this particular example, I need 4 multipliers and 1 adder, 1 subtractor, right? What if we only had 2 multipliers and just 1 adder or subtractor, right? Actually, you know that to do a subtraction, you can just take the inverse, the 2's complement of the number and add it to the to the previous number, right? And so you could be using the same adder, except that for multiplications, right? If I'm going to multiply mod 2 from mod 1, I could take the 2 complements of mod 2, right? And then I add that to mod 1. So you'll be doing the same thing, right? In 2's complement notations, okay? So I could use the same hardware. Right? I could use the same hardware resource, okay? And that it's actually helpful if I am restricted by my resource, because typically you find that in the ALU, right, in a arithmetic logic unit, right, you just have typically just have a adder, right? You don't have adder and subtractor, right? So this is a very real problem, right? What if I have less resource than what I require? Right? Therefore, I definitely need to share, right? That is the bottom line. I need to share, and therefore, when you talk about sharing, you need to schedule, right? So if I have just 2 multiplier and one adder subtractor, okay, what I could do is, well, think of it from a timing perspective, right? So now I can break it into time, right? At time step 1, okay, the 2 multiplier can be used by to multiply A and C, B and D, okay, basically just to compute the real part. Okay, the second cycle, when I am doing the um, adding, subtracting for the real part, I could be doing the multiplication for the imaginary part, right? And then the third clock cycle, I'll be doing the adding, subtracting for the imaginary part. So essentially sharing, right? So you find that the resources at that particular time instance, okay, it's met by the resource. So at this time instance, I'm using 2 multiplier. At the second time instance, I'm using 2 multiplier and a adder subtractor. At the third time instance, I don't use the multiplier anymore. I'm just using the adder subtractor. And just by extending the time, sharing the resources, you can therefore do the computations. Okay, so this data flow graph is trying to look at it from a clock cycle perspective, trying to understand or trying to design your systems, trying to see how the resources can be shared. Okay, obviously you see that, hey, between the first cycle and the second cycle, the multiplier will have different inputs, right? Okay, will have different inputs, right? So for example, in the first cycle, A multiplied by C. In the second cycle, it will be A multiplied by D, right? So one of the input is not the same, right? At cycle 1 is C, cycle 2 is D, right? How do I resolve this, right? How do I enable this in the hardware, right? So naturally you'll be thinking, I need to use a multiplexer, right? I need to use a multiplexer, right? So C and D, okay, will be multiplexing so that they share one of the inputs to the multiplier, right? So in data flow graph, we could be looking at 2 type of view. One type of view with respect to the time or clock cycle, right? The second view could be with respect to the resource. So this graph that we're looking at is with respect to the resource. So by looking at this graph, I know I'm going to use 2 multiplier, I'm sorry, 2 multiplexer, 2 multiplier, and 1 adder subtractor, right? And this tells me how the connections are actually made to all the hardware. Okay, so this tells me the connections as well as the resource. In the previous diagram, it tells me how the connections are made at the particular time in order to make the computations. Okay, so again, just to recap and just to repeat, I can be looking at, in a data flow graph, I could be looking at clock cycle perspective or timing, or I could be looking at resources, okay, which whereby the hardware resource that is needed. All right. Well, so you'll find that this requires some control circuitry, right? So you need, therefore, in a two input multiplexers, right? So two input comes out with one output. You therefore need one control signal, a control bit. So this control bit has to be crafted, right? So basically, the control bit will be select C at cycle 1, so select D at clock cycle 2, right, and so on, right? So how to come up with this signal? You need a basic finite state machine. You need a basic finite state machine. Okay, so a state machine is a ordered flow uh, of coming out with a state machine is, I actually expect you to know what a state machine is, you know. So I think during this week in the tutorials, if you find that you need more clarifications on state machines, please let me know, right? Because it's actually a very basic idea. All right. Right. There's other things that can be done with the data flow. So again, right, data flow could tell me the resources. Well, what if I tells you that we have DSP blocks on the FPGAs that can multiply and add, okay, in the same DSP block, right? So I could combine a multiply and one of the multiplier with the adder subtractor in one block, right? If I can do this, right, so my resource becomes simplified. Okay, how do I rearrange my computations, right, in a data flow diagram? Okay, that will be something interesting to think about, right? How should we map the operations, right? So in terms of think of it, the clock cycle needed, right? So a more fundamental question to ask yourself is, well, if I multiply followed by add, is this going to be done in the same cycle, meaning the same clock cycle, right? If it is, okay, then I'm quite assured that, okay, it can be, this I can be combined and put in one clock cycle. Okay, if it's not, then how many cycles are needed? Okay, so I'm actually giving hints to try to help you to see. Okay, we could incorporate further details into the synchronous design. Okay, well, if I fall back to the original design whereby 4 multipliers and then 2 adder subtractors, okay, if I add in a a bunch of registers, basically add in registers at the output, add in another intermediate registers, okay, in computer architecture terminology, what I've done is I actually added 2 pipes, right? I've added 2 pipes. What I've done is I've broken the computations into stage 1, stage 2, stage 3. Okay, stage 1, stage 2, which is between the 2 cell registers and then the output. Okay, so what it means, it's plain English. Okay, what it means in plain English is that I've added a latency of 2 cycles, right? Meaning, right, when my input changes, it will take 2 clock cycles before the results appear at the output. Okay, so that is really what we've done by adding these 2 cell registers. If I add in one more registers at the input, then I will expect a 3 clock cycle delay. Okay, right? So you need to know, okay, the implications of adding the registers. So what is the advantage of adding the registers? Basically, I reduce the delay, right, between the registers. So previously, right, the worst case timing delay will be from the input of the multiplier all the way to the output, right? By adding an intermediate registers, now I break it up into 2, right? The worst case delay could be from the input of the multiplier to the output of the multiplier, or it could be from the input of the adder to the output of the adder, right? So I would expect the clock performance or the clock speed to be much higher than without this bunch of registers. Okay, right. And then finally, okay, to map the state machines, okay, you will find that usually the state machines you will have uh, a registers, okay, a set of registers, and then a bunch of combinational logics. Okay, so if you need more clarifications on state machines, remind me during the tutorials to discuss them. Okay, I can give you some examples to develop state machines easily. One thing I would like to add further is that typically when we talk about finite state machines, okay, we are referring to two types of state machine. One is more, the others is milli. Okay, more state machine is a very simple state machines, right? It doesn't take in it doesn't depend on any inputs, right? It does not depend on any conditions. Okay, so upon powering up, right, you will go from state 1 to state 2 to state 3 and whatever state, and then at the end of that, okay, it might come back to state 1 again and so repeat. So it's a very sequential one, right? And then you just go from one state to another in a very well defined way. In a mini state machines, okay, you could change from one state to another state. For example, I'm at state 1, okay, I could move to state 2 or I could move to state 5 depending on what is my sensor input. Okay, so a mini state machine is require conditions, require inputs to make the transitions to a different states. Okay, so these are essentially the two types of states in a finite state machines. Okay, so yep, that's what we want to cover, right? And you'll find that for you to control, right, your data flow. So you use a data flow diagram to understand the resources needed, to look at the how the resources are used at different clock cycles, right? So that you can understand the resources usage, and then plan for it. Okay, but you'll find that as we have seen in the examples, okay, when you have less resource, when you do sharing, you therefore need to have control logic. Right? A simple way to do control logic is to use finite state machines. All right. Yeah, and that's pretty much what we want to cover. Okay. So sorry for the 10 minutes delay at the start of this lecture. Okay, I think I'm getting the hang of it. Okay, the next time round when we do it on Friday, I hope you'll be smoother. Okay, and then next time round, let me just quickly check. Is there any questions posted? Um, Seems like there isn't any questions. Uh, right? Seems like there isn't any questions. Yeah. Yeah, doesn't seem to have any comments or questions. Um, right. Okay. I'm actually waiting for the YouTube to complete, right, to see whether we are going to have any questions on the YouTube link. Uh, yeah, I think that's about it. Okay, so I will stop the video lecture now, right? And feel free to post questions onto the forums, right? And let us know what you think, uh, and then ask questions, right? And then yeah. So the tutorials this evening will be as normal, okay, as per normal. Okay, right. Thank you very much.